student. In this video we'll be taking chemistry under the topic periodic table. So let's proceed. So what are the objectives of this session? The students should understand the concept of periodic table. They should understand the groups and periods and their element characteristics in the periodic table. Students should be able to arrange electrons in the main shells and sub-energy levels. They should be able to determine the electronic configuration of elements. They should be able to determine the relative atomic mass of the elements and a host of others. So now let's begin. What do we refer to as the periodic table? Periodic table is a table of elements arranged in order of increasing atomic numbers. It's a table of elements arranged in order of increasing atomic numbers. Modern periodic table is created by a man called Mendeleev. So this is the structure of the periodic table. This is how it looks like. But this is how it looks like. So it contains the elements we have in chemistry. So like what we've learned, we understand what elements are. We understand how they react. So here's the structure of the periodic table. So now what are the key points we should note? We should note that the periodic table has horizontal rows called periods. So now looking at this here, we find out that it is you can actually determine the rows and columns from this. So here is the column, here is the column, here are the columns, here are the columns, while these are the rows. These are the rows. So we need to understand that what the periodic table has horizontal rows called periods. So what it implies that there contain horizontal rows here called the periods. So now what implies that, as you can see, this table is numbered already. We have 1 2 3 4 5 6 and 0. The 1 2 3 4 5 6. So for period 1, the elements are in period 1 hydrogen and helium. For period 2, they are the lithium, beryllium, boron, carbon, because the periodic table, the period are in horizontal rows. For the period 3, we have the sodium, magnesium, aluminium, silicon, phosphorus, and others. For period 4, so that's how you can determine it. So the periodic table has horizontal rows called periods. A group is a vertical column in the periodic table containing elements with the same number of electrons in the outermost shell. Again, a group is a vertical column. It is a vertical column. What that implies that here is the group, here it is a vertical column. So here we have a number of groups here. So the group starts from here. For group 1, we have the group 1, group 2, group 3, group 4, group 5, group 6, group 7, and 0. So the group is the vertical column. So for group 1, we have a list of elements here: the hydrogen, lithium, sodium, and others. Group 2, beryllium, magnesium, and others. For group 3, we have boron. For group 4, carbon, like that. So we have a list of groups here. So now let's proceed. A group is a vertical column in the periodic table containing elements with the same number of electrons in the outermost shell. So when we construct the structure of the shell, so we are filling in the electrons. We'll find now. Let's do that now. So let's do that now. As stated here, we have that a group contains elements with the same number of electrons in the outermost shell. Now let's take two elements that are in the same group. We have the lithium and the sodium. Now let's use that as a case study. We have the lithium I. Oh wait, I need to change the background. Okay, so now we have the lithium I and we have the lithium I and the sodium. So yeah, and what's the atomic number of lithium in the periodic table? So we need to determine that first. So now looking at this here, For lithium, the atomic number is 3, 1, 2, 3. And for sodium, what's the atomic number? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 11. So this is 3 and 11. So now let's construct this in the shell. Now we have this here, the representation of the electrons in the shell. You have this. So so for the element lithium, the arrangement of its electrons in the main shell is okay. We have the this we still explain this. This should be explained later in this video. So now we have the two. Since the atomic number is 3, then 1. Okay. Now for the element sodium 11, we have this nucleus here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, then 11. So now, based on these points that has been highlighted here, we have that a group is a vertical column in the periodic table containing elements with the same number of electrons in the outermost shell. So elements in the same group contain the same number of electrons in the outermost shell. So here, since the lithium and sodium are in the same group, and looking at the outermost shell, which is the one here, the outermost shell, which is the shell here, contains, so based on the key point states, they contain the same number of electrons. And looking at this contains an electron, while this contains an electron. So that has been definitely proved that the elements in the same group contain the same number of electrons in the outermost shell. So now let's proceed. Elements in the same group have similar chemical properties, so we need to know that as well. They have similar chemical properties. The number of the group indicates the number of electrons in the outermost shell of the element in the group. In other words, all the elements in each group have the same valence electron. So what does that indicate? It states that the number of group indicates the number of electrons in the outermost shell of the element. So the number of group indicates the number of electrons in the outermost shell of the element. Again, the number of group indicates the number of electrons in the outermost shell. So now what does that indicate? Looking at this, so the group 1 element, group 2, the group 3, group 4, group 5, group 6, and group 0. So what does that indicate? So for the group 1 element, we have the hydrogen, lithium, sodium, potassium. It indicates that the number of groups indicates the number of electrons in the outermost shell. That means that the elements in group 1 have 1 electron in the outermost shell. Those in group 2 have 2 electrons in the outermost shell. Those in group 3 have 3 electrons in the outermost shell. So now let's demonstrate that. So for example, let's take calcium as or carbon as an example. So let's erase this. You have the carbon. So let's determine the atomic number of carbon. So how do we do that? It's 1, 2, 3, 4, 5, 6, and it's written here already, which is 6, right? Okay, let's erase this and use the white pen. 6. So let's arrange the electrons in the main shell. The nucleus, we have 1, 2, 3, 4, 5, 6. So now we're looking at the outermost shell, which is the one here. It contains how many electrons? It contains 4 electrons. 4 electrons. And definitely carbon is in group 4. The carbon atom is in group 4. So that is it. When we test for each of the elements here, we are going to get the same, except for the element in group 0. We'll get to that later. So So now let's proceed. A group is a family of elements with the same similar chemical properties. So there are groups 1, 2, 3, 4, 5, 6, 7, and 0 in the periodic table. You need to know that as well. So now looking at groups. Now let's begin with the group 1 element. These are lithium, sodium, potassium, calcium, francium. Group 1 elements are called the alkali metals. They are called the alkali metals because they react vigorously with cold water, forming alkali and liberating hydrogen. So the oxides dissolve in water to form strong alkalis. Example elements in the same group have similar chemical properties. So here's an element in group 1. It dissolves, it reacts with water to forming an alkali and liberating hydrogen and liberates hydrogen. The oxides dissolve in water to form strong alkalis. So what are some properties of the group 1 element? They are Charles nitrate 5 salt decompose with difficulty on eating. Sodium and potassium carbonate 4 salts are the only soluble salts that do not decompose on heating. No, let's take that again. They are thiazocarbonates, they are thiazo nitrate salts decompose with difficulty on eating. So they decompose with difficulty on eating. Potassium, sodium, and potassium carbonate 4 salts are the only soluble carbonates that do not decompose on heating. So we need to know that as well. So here is the chemical equation for liter of water has been explained above. So now the group 2 elements, beryllium, magnesium, calcium, strontium, and barium, they are called the alkaline earth metals. So you need to understand that they have 2 electrons in the outermost shell and ionized by the loss of the 2 valence electrons. So they ionize by the loss of the 2 valence electrons. So what does that indicate? So sorry, you need to, okay. What does that indicate? They ionize. They have 2 electrons in the outermost shell and ionized by the loss of the 2 valence electrons. So for the group 2 elements, we have beryllium, which has an atomic number of 4. We have beryllium, which has an atomic number of 4, which has an atomic number of 4, 1, 2, 3. Arrangement of the electrons in the main shell 4. So now what are we trying to get? They are ionized. They have 2 valence electrons. They have 2 electrons in the outermost shell and ionized by the loss of 2 valence electrons. So these electrons here are also known as the valence electrons. The electrons in the outermost shell are also known as the valence electrons. They are also known as the valence electrons. So they are ionized by the 2 electrons. So during chemical bonding, so the topic will be treated later in this channel. These electrons in the outermost shell ionize. They react with other elements. They engage in chemical bonding. So and they lose these electrons. The beryllium atom lose the electrons, form the compound. They lose 2 electrons. The beryllium atom lose 2 electrons to form this charge, to be positively charged. So they lose these 2 electrons to engage in chemical bonding. So that's it. In order to obtain, okay, we'll get to that later in our videos. So now let's proceed. We have 2 electrons in the outermost shell and ionized by the loss of the 2 valence electrons. So here is an illustration. The calcium atom loses 2 electrons to form the calcium ion. So now the group 0 elements are the inert gases or noble gases or rare gases. They are helium, argon, neon, krypton, xenon, and radon. They are inert or highly unreactive because they have their outer shell completely filled with electrons. They are inert or highly unreactive because they have their outer shell completely filled with electrons. What does that indicate? So now let's take that again. Pardon. Group zero elements are the inert gases or noble gases or rare gases. They are helium, argon, neon, krypton, xenon, radon. They are inert or highly unreactive because they have their outer shell completely filled with electrons. They have the outer shell completely filled with electrons. So now, looking at the diagram here, so now an example of an element in group 0 is neon, which has an atomic number of 10. It has an atomic number of 10. So it has an atomic number of 10. So now let's represent this in the main shell. Let's represent the electrons in the main shell. We have 1, 2. This is the nucleus. 1, 2, 3. Oh, sorry. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So now for the elements in group 0, they do not have, they completely occupy the electrons in the outermost shell. We realize that for most of our elements, the outermost shell are usually not complete. For example, you might have helium because it's completely filled with 8 electrons. So it indicates that their outermost shell are completely filled. The outermost shells are completely filled with 8 electrons. For example, for an element like beryllium, we have 1, 2, then 3, 4. This falsely indicates is in group 2. So, and we notice it's not completely filled with 8 electrons. So that's what we're talking about. For the group 0 elements, their um their outermost shell is, their outermost shells are completely filled with 8 electrons. So now, because and their inners are highly unreactive because they have their outermost shell completely filled with electrons. So those are the group 0 elements. For now, the transition elements are all metals. They are called transition metals because they use electrons from both the inner and outer shells for chemical combination. They have variable valencies and are therefore used as catalysts. So during chemical combination, the electrons here, for instance, for an element like beryllium, we have 2, 3, 4. For an element like beryllium, it uses the 2 electrons to engage in chemical bond. But for the transition elements as stated here, they use the outermost shells and the inner, they use the outermost the valence electrons and the penultimate electrons and the electrons in the inner shell. The mix use of the electrons in the inner and the electrons outer for the transition elements. So that's what is stated here. And they have variable valencies and are therefore used as catalysts. An example is iron 2 and iron 3. So now let's move to periodicity. What's periodicity? Periodicity is the regular patterns or trends in which the physical and chemical properties of elements occur when the elements are arranged according to their atomic numbers in the periodic table. Let's take that again. It is the regular pattern or trend in which the physical and chemical properties of elements occur when the elements are arranged according to their atomic numbers in the periodic table. Periodic table states that, so what does, so the periodic law, so the periodic law states that, now let's look at the periodic law. It states that the properties of elements are the periodic functions of the atomic number. So we should get to the theoretical aspect of this, or the practical aspect of this, whereby we understand better. So now let's look at the arrangement of electrons in the main and sub energy levels. So in an atom main shells a lettered key element. In an atom main shells a lettered key element. What does that indicate? It indicates that, let's take beryllium as an example. So here is it shell. So in an atom main shell, in an atom main shells are lettered KLMN. So it indicates that, okay, let's erase this here and do this. So it indicates what? K, oh sorry, KLMN. So here is it. So here is it, the K, okay, sorry, the K L and we have the N here. So so atomic shells are lettered KLMN. Okay, it is lettered outwards from the nucleus. So here is the nucleus. Here is lettered outward from the nucleus, and they corresponded to main energy level 1, 2, 3, 4. So and they correspond to the main energy level. So we need to understand that this letter, these main shells, yeah, KLMN, correspond to the main energy level, which indicates that this has 1 energy level, 2, 3, and 4. Okay, now let's proceed. The maximum number of electrons in a main shell or in each main energy level is given by 2n raised to 2, where n stands for the number of the main energy level. Get to that. So now look at this arrangement of electrons in the main shells. Thus, for the main energy level, the maximum number of electrons it can accommodate is 2n squared. What does that indicate? Now, the maximum number of electrons the K shell can accommodate, the L can accommodate, M and N can accommodate is what? 2n squared, where n represents the energy level, which is this here, which are the ones here. So now let's proceed. Okay, 2 times that is 2 times n times n. So for the K shell, which contains 1 energy level, it can contain a maximum number of what? For the K, contain 2 times n square, which is 1 square, which is going to give us 2 times 1, which is going to be 2. So it's the maximum number of electrons it can contain is 2. So for the L, we have, okay, for the L we have 2n square, then 2 times 2 square as contained here. That's if 2 square is 4, then 2 times 4 is 8. So the maximum number of electrons it can occupy is 8. So for the shell, which is 2n square, then we have 2 times 3 square, which gives what? 18. So we need to understand that. And for the n shell, which is 2 times 4 square, which is 32. So that is it. So now let's proceed. Now before we get to this, we need to understand how we can represent the electrons in the main shells, how we can arrange our electrons in the main shell. Now I think I've explained that before. Now let's take that again. Let's take an lithium as an example. Now, how do we represent lithium in the how to represent the electrons of lithium in the main shell? We do this. We construct this, whereby this is our nucleus. So for the K shell, which is the first one here, it can only contain a maximum number of 2 electrons. So now, and we know that we need to determine the atomic number of lithium, which is 3. So now it starts by filling in the electrons 1, 2. So it still remains 1. Then now let's conjugate the 1, 1. That's it. Now let's take another element. Let's say you are writing for oxygen, which is 8, atomic number of 8. So we have what? 2 first for the K shell, 2 for the L, or for the other we have 2. Then the next is it still means 6 electrons. So now let's fill that. You have 1, 2, 3, 4. So this contains 2 2. This holds 2 2. We need to hold them 2 2 here, unlike this here. So 6, 1 2 3 4 5 6. Okay, so that is it. It is until it has gotten to 8 we will no longer feel electrons here. So here is how it's represented. Now let's check for another element like magnesium, which is 12. Now how do we do that? We say 1 2 3 4. Okay, sorry, 3 4. Okay, 1 2 it still means 10. So then 1 2 3 4. Now complete, let's fill them. 5 6 7 8. So that's 8 there. We need to now write out another. We need to now write out, draw hand the circle around it. Then since we have 2 and 8 here, then that's 10. Then it remains 2 electrons. That's 2. So that's how we can actually construct them. So now let's make use of the final one, which is calcium, and it has the atomic number of 20. Then we get what from here? 1 2 3 4. Okay, sorry, 1 2 3 4 5 6 7 8 9 10. Actually we need to do this again. 11 12 13 14 15 16 17 18. Oh, it remains 2 here. Then 19 20. So that's how we actually, that was how we are supposed to do it. So now let's proceed. Now let's look at subshells or orbitals. So what do we refer to as subshells or orbitals? Now each main shell is made up of one or more subshells or suborbitals. Each main shell is made up of one or more subshells or suborbitals. So an orbital is a space around the nucleus. An orbital is a space around the nucleus where there is a probability of finding electrons. So there are S, P, D, and F types of orbitals. We need to know that there are S, P, D, and F types of orbitals. There are 3 p orbitals, which are, so under these we have 3 p orbitals, which are the 2px, 2py, and 2pz orbitals. So the energy of electrons in a given subshell is different from the energy of electrons in other subshells. So what does that indicate? In the s orbital, the energy of electrons present there is different from the energy of electrons in the other one. So now let's proceed. The subshell with the lowest energy is called the s subshell. The next higher energy is called the p. The next p orbital or subshell, the next higher energy subshell is called the d subshell, while the next higher energy subshell or orbital is called the f subshell. So there are limited number of electrons which can be accommodated in each subshell. So we need to understand that there are limited number of electrons which can be occupied in the main shells, there are also limited number of electrons which can be occupied in each subshell. For s orbital, the maximum number of electrons it can accommodate is 2. The p orbital can carry a maximum of 6 electrons. You need to understand that the d orbital can contain a maximum of 10 electrons, while the f orbital can accommodate a maximum of 14 electrons. So you need to understand that. So now let's get into the electronic configuration now. That will be linked with this subshell. The electronic configuration of an atom is the arrangement of electrons in the orbitals or subshells of the atom. So the electronic configuration of an atom is the arrangement of electrons in the orbitals or subshells of the atom. So now the physical and chemical properties of an atom depend on the arrangement of its electrons. So we need to understand that the physical and chemical properties of an atom depend on the arrangement of its electrons. Orbitals with lower energy are filled with appropriate number of electrons before orbitals with higher energy. As has been stated here that the subshell with the lowest energy is called this, next is this, next is, so what this indicates is that we need to completely fill the s orbital before we get to the p orbital and move gradually in the manner. So the orbitals with lower energy are filled with appropriate number of electrons before orbitals with higher energy. For example, the 2s orbital is filled completely before the 2p orbitals as this, okay, while the f orbital can accommodate a maximum number of 14 electrons. So now the electronic configuration, the arrangement of the orbitals according to their increasing energy is this. So we need to know, understand this, we'll get it, we'll put into practice this soon. So the arrangements of the orbitals according to their increasing energy is 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 5 4 4p, 5s, 5 4d, 5p, 6s, 4f, 5d, 6p, 7s according to their increasing energy. We need to understand this, so which indicates that the electrons are completely filled here before moving on to the next one, now the next one, to the next one, to the next, and next, like that. So and here is the increasing energy level, which is 1s, 2s, 2p, 3s, 3p, 4s. So we need to understand that. So now let's proceed. The electronic let's look at the electronic configuration of the first 20 elements. The electrons in an atom occupy orbital in order of increasing energy level. The electrons in an atom occupy orbital. Electrons in an atom occupy orbital in order of increasing energy. This has been repeated severally. So now the orbital or shell nearest to the nucleus is the one with the lowest energy. Okay. Writing of electronic configuration of atoms of some elements in the ground state can easily be done by filling in electrons to the orbital starting with lowest energy subshell. Okay, we'll get to that later. This ground state of an element is its most stable state. So the electronic configuration of an atom of an element with the atomic number 7 is this. So please wait. Okay. Now the electronic configuration of an atom of an element with the electronic configuration is 7, or with the atomic number 7 is this. Again, the electronic configuration of an atom of an element with atomic number 7 is this. This implies that the subshells are listed in order of increasing energy, and the numbers 2 and 3 are added to show the number of rows on each orbital, and the numbers 2 and 3 are added to show the number of rows of electrons on each orbital. Let's take that again. This implies that the subshells are listed in order of increasing energy, and the numbers 2 and 3 are added to show the number of electrons on each orbital. So now let's put into practice this. So now looking at this now, the electronic configuration of an atom of an element with the atomic number 7 is this. So now let's write this out. With the atomic number 7 is this. So we have here 1s2, 2s2, um and 2p3. So here is the electronic configuration of an element with the atomic number 7. What does that indicate? It indicates that the arrangement of the electrons in the orbitals is the electronic configuration, and here it is. So now how do we now represent electrons? How do we represent um electrons in the orbitals of subshells? So now let's take this now. So here is the increasing energy level of here is the order of the increasing energy level. So we need to understand this now. Let's take hydrogen as an example. Hydrogen has an atomic number of 1. So how do we represent, how do we accomplish this? The statement here. So how do we write out the electronic configuration of the atom? So you say 1s, as stated above. It was stated that it has been stated the maximum number of electrons these suborbitals, these SPDF orbitals, the subshells, the maximum number of electrons they can contain. So now let me state that again here. For the S orbital, it can contain a maximum number of 2 electrons, a maximum number of 2 electrons. For the P orbital, it can contain a maximum number of 6. It can contain a maximum number of 6 electrons. For so now let's work with this first. So now for the hydrogen atom, we say one start with 1s, 1s1, because the value here indicates the atomic number. The value here 2, 2 and 3, when they are added up together, it must give the atomic number, the value of the atomic number of the element. So now 1, which is the atomic number of hydrogen. So here is the electronic configuration of hydrogen. That is it. So for helium, which is 2, we have 1s2. That is it. For lithium, which is 3, we have 1s2, since the maximum number of electrons that can be contained by s is 2. So we have 1s2. Then move to 2. What's the next one? 2s here. Then 2s1. That's 2 plus 1, which is 3. So for beryllium, which is 4, we have 1s2, 2. Okay, after this 2, it still remains 2 here, and this can the 2s orbital can still contain that 2s2 can still contain the 2 electrons. So here is the electronic configuration of beryllium. So for boron, which is 5, we have 1s2. Okay, then next is what? 2s, right? Then 2s2, 2, 4. It still remains about 1 electron. So what's next here? We have 2p, then 2p, what? 1. So that is it. So now let's move to advanced one, task. So for, let's take magnesium as a case study, or as an example. Magnesium, which has an atomic number of 12. So the electronic configuration should be 1s2, okay, 2s2, yes, that's 4. Okay, for the 2p, what is it? This can contain the maximum number of 6 electrons. So when 6 is written here, we have 6 plus 2, that's 2 plus 4, 2 plus 2, which is 4, 4 plus 6, which is 10. So it still means 2 electrons. Then what's next here? 3s, then 3s2. So that's for magnesium. Now for let's take an example for aluminium, which is 13. So what do we just add? We have 1s2, okay, 2s2, 2p6, 3s2. Since this cannot contain any longer electrons, it can't be 3s3 to make it 13. Yeah. So what do we do? Move to the next one on in the energy level, which is 3p. Then write 3p 1. So we need to understand how that is done. So now take a careful look at the ground state of the electronic configuration of the first 20 elements. So let's look at this carefully before we move on. So now, the relative atomic mass. Let's look at the relative atomic mass based on the carbon 12. How you can determine the relative atomic mass of some element. The mass of an atom is an extremely very small and inconvenient fraction. It is therefore preferable to express atomic masses by comparing them with the mass of the standard mass. Relative atomic mass of an element has no unit because it is a ratio, but atomic mass of an element is expressed in grams. So now let's take that again. The relative atomic mass of an element has no unit, but because it is a ratio, but atomic mass of an element is expressed in grams. Now, okay. Now, from the definition of relative atomic mass, one might think that all elements would have whole number masses. No, in fact, relative atomic masses are rarely found to be exactly whole numbers. In fact, relative atomic masses are rarely found to be exactly whole numbers. This is because most elements have two or more naturally occurring isotopes, and the relative atomic mass takes into account the abundance of each isotope. For example, chlorine has approximately 75% of an isotope with maximum mass number 35 and 25% of an isotope with mass number 37. Therefore, the relative mass of chlorine is found to be 35.5. So now what we want to determine in this session, in this segment of the video, is how we can determine the relative atomic mass of elements. So now, how can we determine the relative mass of chlorine when this value has been given to us? The chlorine has approximately 75% of an isotope with mass number 35. So it is indicates that, okay, let's clear this here. You know, we have chlorine, the isotopes of chlorine, we have 35, mass number 35, and we have the one of mass number 37. And it is stated that as approximately 75% of an isotope with mass number 35. So this 75% here. So for and 25% of an isotope with mass number 37. 25% of an isotope with mass number 27 is this 25%. Therefore, the relative atomic mass of chlorine is found to be. So how do we calculate that? So we need to get the ratio of the percentages of the isotope. We need to get the ratios. By doing that, when we know this 75, the ratio of this can still be simplified. When we say 75 divided by 25, you can still get 3 out of this, which will be 3:1. We need to obtain the ratio. So then what's next? Then get the total ratio, and we have the total ratio as 4. 3 plus 1, which is 4. So what do we now do? We say we apply this formula. Okay, this will be explained here. So here is the formula we are going to apply. The relative mass of X is the mass of the first isotope times 1 plus the mass of the second isotope times 3 over total ratio. What does that indicate? It indicates that now when we are comparing it with what we are doing right now, we say the relative atomic mass, which is R.A.M, is equal to this, the mass number times the ratio, which is 3, plus the mass number of the other one, which is 37, times the ratio of this, which is 1, divided by 100. So that's what as divided by the total ratio as done here. So divided by the total ratio, sorry, which is 4. So when we solve this, we're actually going to get this here, which is 35.5. Now let's move to an exercise. An element X has 2 isotopes present in the ratio of 1:3. What would their relative atomic mass be? how do we determine it? We have the two isotopes here. Their ratio has been stated here 1:3. So the total ratio is 4, and the relative atomic mass of S, definitely the mass of the first isotope X, which is this times the ratio here 1, there is it, the first one, and times this here, and the mass of the second, which is 22, times 3 the ratio over the total ratio. Then you solve and get 21.5. So now question 2, the mean atomic mass of chlorine is 35.5. Chlorine has two isotopes of mass 35 and 37. What's the percentage composition of the isotope of mass number 25? So what have we had to get? So we need to understand this question. For those that don't have any knowledge of mathematics, they are going to find it difficult to solve a question like this, but just follow me and remain calm. So now, what have we had to calculate? Since the mean atomic mass has been given to us, which is the relative atomic mass, so the data given, we have the relative atomic mass as 35.5, and we have the atomic mass as this, and it stated that the chlorine has two isotopes of mass 35 and 37. So we have the mass numbers as 35 and 37. Okay, let me write that here. The mass number of the first 35, and mass number of the second, which is 37. What is the percentage composition of the isotope of mass number 35? What is the percentage of the composition of the isotope of mass number 35? So how do we determine it? We have to calculate the composition of the isotope of the composition of this of mass number 35. So based on our knowledge, we can deduce that what we can deduce, okay, based on the knowledge we've acquired, we can deduce that for this year, looking at this year, we will find out that this 75, the percentage isotope, the percentage composition of the isotope rather, gives us 100. The sum gives of 100, which is 75 plus 25 gives us 100. So now we can actually deduce that you can say let the number of atoms be 100. Now after doing that, then we can actually say let the number of atoms of the chlorine, which is the percentage composition, that is still referred to as the percentage composition of the chlorine atom of mass 5 be A. If this is A, then definitely the other one will be 100 minus A, which indicates that when A is added to 100 minus A, we are going to get 100. So that means if this is A, the other one will be 100 minus A, since their sum give 100. So now you say A atoms have 35 units each. Okay, so and 10 minus A atoms have 37 units each. So we've actually gotten our answer. Then we can actually make use of the formula here by saying the mass of the first isotope times 1. Looking at this, we have the mass of the first isotope here, which is 35, times the ratio, which is A. That is it. So the ratio, which is A, we've gotten A already, plus the mass of the second isotope times the ratio or the percentage composition, the mass of the second isotope, which is mass 37 times 100 minus A for this year. This is it here. So over the total number of the percentage composition, which is 100. So and you know this gives us the relative atomic mass, but this has been stated in the question already, which is 35.5. So we solve this like this, then we get our answer. You solve it mathematically, and we get this here 75 isotopes. So what does that indicate? In percentage, we have 75 atoms over. So just convert it to the percentage fraction, to which is 35%. So that's it. It's very simple. You need to understand how it is done. So you need to solve more questions on your own. Thank you very much for watching. If you find anything difficult, you can send an email message to hsunny507@com. Do not forget to like, subscribe, watch, share. Thank you very much for watching. I highly appreciate you.